All right. So let me say this again. What we're going to study now in chapter 9 is what do we do when the population standard deviation is unknown when we're trying to estimate a population mean. We can no longer use sigma in our formula for the standard error, which is sigma divided by the square root of n. In its place, we have to use S, the sample standard deviation, and divide that by the square root of n. But the z critical value, we're calling it a critical value, the z that we multiply times the standard error to give us our margin of error, is no longer being used when we replace sigma with S. We're going to replace it with another distribution that we're going to learn about tonight called the T distribution. All right. So now I think I can talk about it. So now you can't see this yet, but I'm going to open up Cengage. Just give me a second to do that. All right, and then we'll spend probably the whole time talking about the T distribution and also about how we do a confidence interval using the T. All right, so let's end up finding it. And I believe I picked the wrong, what happened here? I picked the wrong book. All right, so give me a chance here to go back. Sorry about that. My other course, I might have told you this, my other course also uses Cengage. And so I have two textbooks, and sometimes I forget which one is which, and I sign one with the wrong one. Okay. So, just give me a sec here, and I'll get signed in. All right. Cengage is giving me problems right now because they're taking me to the wrong sign-in sheet. Sign-in thing. All right, hold on. Sometimes it does this. All right, let me try this. Okay. All right, sorry about this. It's just ridiculous. I hate Cengage. They change the websites like every day. All right, now see, I can't even sign on where I'm at. It's ridiculous. All right, sorry about this. It's just. All right, try it again. I don't understand why these companies. Let me see if I have the right one. They fool around with their websites every day, and it's and then they don't show the same thing every day. Ridiculous. Really annoying. All right. There we go. This one here I want. Oh, now I'm getting an application error when I get to it. They must be doing something to their website right now. It's really annoying.
You wanna restart?
Huh?
You wanna restart your computer?
No, it's not my computer. It's their website. It's their website, not my computer. Sure. All right, I got it now. All right. There you go. Now, Han, you should have seen you should have seen a year ago when I was using Cengage. They bought this new program. Unbelievable. Unbelievable. The homework system didn't work for half the students in the class for a whole semester.
Oh.
And then they would register for it, and then one day they wake up and they go into it, and they would say they're not registered anymore. And then I would get on, and we spent, each of us, the student and myself, we spent 2 hours on the phone for them to fix it. And it would have multiple times. I must have spent 30 hours with Cengage. I actually told them, I will never use your products ever again. You're a horrible company. I told them. And here I am using it again. I'm using their stuff again, and then this reminded me of it. It's just like, well, this is minor compared to that. That was, oh my God, I lost all my hair, I think, that semester. I think the fact that I don't have hair now. I had hair before then, I don't have it. All right. Now, now the students' T distribution. We do have a link to this. I'm afraid to link it because it'll probably take me to some other universe, but I'm going to do it anyway. Oh, here it is. It's just right below. All right. So can you see the screen? You see it all right? All right.
Mhm.
All right. So it says here, it is rare that we know the standard deviation of a population. That's what I've told you, right? And we have no knowledge about its mean. Well, confidence intervals are supposed to be there to estimate the mean. So it says the techniques of the previous section are much less likely to be used in practice. Absolutely correct. So when the population standard deviation is unknown, it must be estimated by the sample standard deviation S. All right, I just told you that. For such applications, there is a continuous distribution called the student's T distribution, and that's what we use to find the critical value. All right, now the T distribution is a family of continuous unimodal bell-shaped distributions. Some of them look just like the normal. They look like the normal. The difference is that for many of them, the tails are fatter. If you could picture, the normal distribution sort of tails off to the left and right. Picture the tails taking longer to get to the left and right. All right, they're fatter. All right. So the T distribution has more variability to it. And that is used because the idea is that if we're replacing the population standard deviation with the sample standard deviation, that what we're doing is basically introducing sampling variability into the standard deviation now. All right. Before it was sort of fixed. We had a population standard deviation. It's supposed to be, as I said, the Fisher approach says, there's one number, right? Population value and the population standard deviation are fixed, period. That's what Fisher says. The more I say it, the more ridiculous it sounds. But if we don't use the population standard deviation and we're replacing it with the sample that we have, the one sample standard deviation, and as you know, it changes from sample to sample, right? Not only is the mean going to change, the standard deviation changes too. So we're introducing sampling variability, and therefore we need to allow the confidence intervals to be a little broader to compensate for that additional variability. All right. And that's what the T is giving us. It's giving us more variability because the T, when you would calculate it, is the T value for a particular level of confidence. The T is always going to be bigger than the Z. All right. It's just going to be. And Now, if the sample size n gets large, then it starts approaching the z-value. It gets close to it, but it will never be this equal to the z-value, and it will never ever be less than the z-value. It'll be always bigger. So that variability is introduced so that we can accommodate the variability from the fact that we're using just one sample, and that's why it's being used. Now, there might be other statistical reasons. Maybe if somebody with a PhD could sit down and give you some technical reason for it, which would be beyond the scope of this course and maybe beyond the scope of my master's degree. But it doesn't matter. This is what's being used. And actually, the reason why it's being used is that a t, remember what a z is. Remember, a z-score is the mean, the sample mean minus the population mean divided by the standard error. If we're replacing the standard error with s divided by the square root of n, maybe this is the reason, all right? That becomes the standard error, right? When we don't know the population standard deviation. By definition, the student's t is a t-score. It's the sample, it's right here. It's the sample mean minus the population mean divided by the standard error. And it's s divided by the square root of n. It happens to match what we need. We need s divided by the square root of n to be our standard error if we're replacing sigma with s. So the t fits the bill, all right? It fits the bill, and it's a t-score. Now here's the deal. The t distribution always has a mean of 0. It's like the z, standard. It's like the standard normal. But the standard deviation is always bigger than 1. It's not equal to 1. It's bigger than 1. Remember? Because I told you it's more variable. So you might ask, all right, if the mean is 0 and the standard deviation is some number bigger than 1, what do we use? Is there some particular value of the t that we use? If we, like with the normal, we say, all right, I need the mean and I need the standard deviation, those two things, right? That determines the normal that we have. What determines the t? Because we're being told that there's a family of t's, right? There's a family of them. That means there's many of them. So what determines which t that you have? It's the sample size. That determines it, the sample size. And specifically, what we use for the parameter is called degrees of freedom. Degrees of freedom. We call it df for degrees of freedom, and it's equal to the sample size in this particular case, the sample size minus 1. By the way, in more advanced statistics, we do have degrees of freedom for everything that we're estimating. I mean, everything. And it's not, most of them are not with this formula. They have more complicated formulas for all of them. They're all different, all right? But for this application, when we're only estimating one thing, the mean, the sample size is going to be, the degrees of freedom is going to be the sample size minus 1. And actually, when I show you the what we plug into in Excel, we look at Excel. Now obviously we can use Minitab for finding confidence intervals, but I want you to learn how to do confidence intervals without having to use some formula. I want you to actually construct them. All right, that is, you have the two pieces of the margin of error. You have the standard error and you have the critical value. And then you multiply them and you get your margin of error. And then you add and subtract from the mean, the sample mean, and you get your confidence interval. All right. I want you to learn how to construct it that way before you start using software and all of that to just give you the answer. That's what most students, right? They just want, I don't want to learn all this. Just show me how to get the answer. But you guys obviously want to know how it's constructed, right? You want to learn how it works, because if you learn how it works, then you'll understand what it means, right? As opposed to just memorizing something and then passing a test and then you forget about it. So degrees of freedom is the only thing that's required to determine the t-distribution. And of course, degrees of freedom depends on the sample size, n. All right. Okay. Now, what does degrees of freedom mean? If we have if we're finding the average, let's say the sample size is 50. We have 50 people, and we're averaging 50 values to get the sample mean, right? 50 values. If we know the sample mean, how many values do we need from the 50 to know what that 50th value is? Well, the answer is 49. If we know the mean, we only need to know the other 49 of the people's values. You can figure out the 50th person's value. That person's fixed, right? That's what they mean by degrees of freedom. It's how many flexible values do we have, all right? In this case, 49. We have 49 values that can change because the 50th value is going to be fixed, all right, based on the mean that we're estimating, all right? So that's what they mean by degrees of freedom. Okay, so you have to remember that it's sample size minus 1. Now, if we were estimating more than one parameter, if we were estimating maybe 2 means, right? 2 means, then it would be n minus 2 would be our degrees of freedom because we're estimating 2 means. Right. So anyway, so it's pretty easy to use, and you know here's your t-distribution with 6 degrees of freedom. Notice it's a flatter curve than the standard normal, but as you increase the degrees of freedom, it starts to get less flat. It should be less fat on the tails, and starts to approach the standard normal curve. Now, just like the standard normal curve, standard normal distribution, T also has tables that were used for many years before there were computers and software. But now we use, obviously, software, right? But they have these tables, all right? And what are these tables? If you see a table like this, and you're wanting to know, find the t, right, where the area to the right is what? Well, 0.10, 0.05, 0.025, 0.01. Now, you got to be careful with using these tables, because if you wanted a 95% confidence interval, right? The tail to the right is going to be 0.025, not 0.05. Because you're still wanting a confidence interval with the area in the middle. So 95% is the area in the middle. The right tail is going to be 2.5. So this is the column that you want for a 95% confidence interval. This is the column that you want for a 90% confidence interval. All right, you get the idea? This is the column you want for a 98% confidence interval, because the area to the right is 0.01. This is what you want for a 99% confidence interval, because the area to the right is 0.05. All right, and the 0.10, the area to the right is 0.10. That's for an 80% confidence interval, right? Because the tail is going to be 10%. On each tail would be 10%. So alpha. All right, let me make sure that's right before I might be wrong about that. Hold on a minute. No, that is the right tail area. Alpha is the right tail area. All right. Yeah. So yeah, that's what it is. So if they're saying if for a right tail area of 0.025, degrees of freedom of 15. So this is the way you would read it. You would go down to 15 degrees of freedom. And 2.131 is the number right here. See it? 2.131 right here. All right, degrees of freedom, 2.131, which means a sample size of 16. Okay, right? Sample size is 16. So I don't encourage you to use tables. You could easily make a mistake, right? You could pick the wrong one. So how do we do with Excel? So stop sharing for a second. Let's go into Excel. All right, let's just pick Excel. All right. I don't want to show you that. What I just showed you is something you should not be seeing.
Did I miss something?
I won't say. Now, suppose we wanted to use the t-distribution in the same way as we use the standard normal. All right. So, let me just say, yeah. So I'm going to put t down here. I guess I'll just add another section down here. We'll call it the t distribution. All right, and I'll do the, again, I'm going to put those 3 types here. Oops. Greater than, oops. Oh, wait a minute. I'm putting the wrong thing here. Where are you guys? Here. Where is, oh, here we are. All right, so this is greater than and between. All right. Now, what if we wanted to do, so I'm going to put over here T1 and T2, right? T1 and T2. What else do I need? Well, we'll find out in a second. I believe we need n, or degrees of freedom, but let's see what the Excel says we need. We're going to do equal, and I'm going to type in T. And there it is, T distribution. See it? Now they do have 2 tails and right tail and left tail. I would just stick with the T distribution. If you want to use 2 tail, you can, but you got to be careful. All right. I'm just wondering if we should do that. Maybe we should just use T distribution for now. So what are we being asked for? We want to, now, if I know what X is, I can find, and know the degrees of freedom, I can find a probability, right? That's what I can find, the probability. But in our case, in a confidence interval, we're not being asked to find the probability, we're being asked to find the t value. So we need to use inverse t, right? Because if we know the area to the left or right, whatever it might be, what's being asked for here, then we want to use inverse t. So anyway, I'm going to leave that alone for a minute, and I'm going to put inverse t somewhere on here. So let's just put it over here. Inverse t. And let's see if we do inverse t, see if it works. Inverse t. No. T inverse. See if there's anything called t inverse. And it is. There it is. See it? T inverse, t dot inverse. All right. And they have a t dot inverse for 2 tails, but I'm going to try with the 1 tail. Now, it's asking for a probability. That would be the probability to the left. But if you want to make it easy, if you know what the right tail is, just say 1 minus the area to the right. That would be your left tail. So if you know for 95% confidence interval, the right tail is 0.025, just type in 1 minus 0.025. It's 0.975, but just so that you don't make a mistake. All right, so 1 minus 0.025. And then let's say the sample size is 16. We said 16 right before. So we'd say degrees of freedom is 15. And now we're going to close our parentheses and hit enter. Now, also, I think oh no, it's going to give us that probability. I think we don't need anything else. It's going to give us our critical value. 2.1314 or 5. See that? It's the same number as you saw on the table. This is an exact answer. Tables are approximate, all right? This will give you the exact answer. So that's how we find a critical value. So I think, I mean, it depends how your brain works, but if you think of a confidence interval, think about the tail. Now let me actually use the inverse T two-tail thing. And I just want to see if it's easier to use for this particular case. So inverse T, and I'll just say two-tail. All right, let me just see what shows up with that. Inverse, excuse me, T. Inverse two tails. Let's try that. Now, my question is, what are they using for probability here? Could they be using the middle probability, the probability in the middle? I don't know. I'm going to try it. No harm trying, right? So I'm going to put 0.95 here and see if it gives me the same critical value. I might be wrong. Might be completely wrong about it. No, it doesn't. So I would stay away from this. Don't even bother with it. Just use the good old inverse T and know that the area that we want is the area to the left, and it's 1 minus the area to the right, if you want to write it that way. All right. It's up to you. That way you don't make a mistake. All right. Because what is the area of the tails? 1/2 of the difference between 100% and the level of confidence, correct? The area of each tail is 1/2 of 100% minus the level of confidence. So that's your right tail. So say 1 minus that, and you have your area to the left. Okay. So if you don't mind using your brain to just figure out the area to the left, you can just put in the number. But if you do 1 minus the area to the right, for some people, that's just easier. All right. So now let's try something else. I'm going to make the degrees of freedom bigger. I'm going to make it 150. All right. Now we know that the Z for a 95% confidence interval is 1.96. Notice the number is getting close to 1.96. You see it? 1.976. Let's make the degrees of freedom 550, just for the fun of it, and see if it gets even closer. And it does. 1.964. And then I'm going to say, let's assume, there's 3,000 people, 3,001 people in our sample. So let's make this 3,000. And it doesn't quite get to 1.96. You see how it gets closer and closer? But it will never get to 1.96. If I put degrees of freedom and just add a few zeros there to make it like, what is that, 30 million, whatever that is, big sample. Well, you know what? It does get below. But you know what? Z critical value. Let's do the Z critical value. Let's do an inverse Z. So I'm going to do the Z inverse Z. And I want to show you the exact value for the Z critical value. So we're going to do Z inverse. I think isn't it Z inverse? Z inverse, or is it not? Or is it inverse Z? Inverse. No, it's inverse normal, isn't it? Normal inverse. There it is. It's not. Yeah, that's what we have to use for the inverse Z, inverse norm inverse. And here, let's put in 1 minus 0.025 or 0.975. Let's see, 1 minus 0.025. And then we're going to put a mean of 0 and a standard deviation of 1. That's our standard normal. Notice the numbers are exactly the same, right? The inverse T, but if you go out to more than 6 decimal places, for example, if I decide in this column here, or these two values here, if I decide to make the decimals to be how many decimal places? Let's make it 10 decimal for the fun of it. Okay. Well, that's interesting. As you can see, the inverse t is still, the t value is still bigger than the z. You see it? You go out to the 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7th decimal place, you see inverse t has a 4 and this has a 3. All right. So the inverse t will never equal the inverse z for standard normal. That's what I'm trying to show you. As you get closer and closer, as your sample size gets bigger and bigger, it'll approach it, but it will never, ever equal the z value. Now, for all practical purposes, if we round to 2 decimal places, they're going to be equal to each other. All right. But I just wanted to show you that I made the sample 30 million. You know, you'll never see a sample of 30 million of anything, but I made the sample size 30 million, or the degrees of freedom 30 million. And even with that large of a sample, 30 million and one, the t is still larger than the z. All right. And that's all I'm trying to show you there. That's all. Did that make any sense to you, what I'm saying?
Yes.
Okay. All right. So inverse t will give us what we want, which is the, and the only thing that you need here is what? You need to, we notice up here I have already a cell for n, right? Up here. You see that? So if I wanted to use this for my critical value, again, I'm going to use t inverse. And I want to put in a probability, right? So where am I going to put that? I don't care. I guess you could just type it right in, or we could just put it below here. So we'll call this I5. Let's put it in there. And then degrees of freedom is going to be this number minus 1. All right. So it's pointing to I5. All right, this number, this here. And so suppose I put in, what am I going to put in? Oh, you know what I'll put in? I'll put in level of confidence. Level of confidence. All right. And so in I5, I'm going to put in 0.95. And then what am I going to put in here? I'm not going to put I5 in there. I'm going to put parentheses 1 minus I5, close parentheses, divided by 2.
Mm-hmm.
Right? Is that right? Did I do it right?
I believe so.
And no, I think you should add another 9.95.
So I didn't do it right, right? So I put in the wrong number. So what should I
feel
put
like
in here? Yeah. Now that what I just calculated is
Oh.
0.025, so I should put 1 minus that.
Yeah.
Yeah. So I'm going to put next to the parentheses. Actually, I should put a parentheses around the whole thing there. Making a mess of this. And I should just put in 1 minus that, right? 1 minus that. There it is. 1 minus that. See if that comes all right. Okay, that's right, right? 1 minus this thing, which is, right? That gives me the area to the left. All right, so that formula there that I just entered will work. I just have to put in my sample size and my level of confidence, and it calculates my T critical value. So I'm going to actually call this here T critical. All right, there's my T critical value. What if I wanted a Z critical value? Let's say for a proportion. So if I wanted a Z critical, the formula would be similar. Well, I want to use norm inverse, right? Norm inverse, this one here. And the probability again is going to be 1 minus, it'll be the same idea, right? It would be the same formula. Actually, hold on a minute. Make this easy. I'm going to put I5. I'm going to put those dollar signs around these here so it fixes those position. Always remember about those dollar signs just so that you know you're fixing the position. All right, so I just fixed everything, and so I'm just going to actually, the easiest thing to do is just copy this down, right? Copy, and then just fix it a little bit. And in this formula here, just change this to norm inverse. Norm inverse, and then instead of degrees of freedom, right, I'm going to put 0, 1. There we go. That's the 1.96 right there, right? Yeah. I didn't want to recreate that formula again with the complicated looking formula. So, all right. So now I have for a sample size of 50, I have my standard normal critical value. And if I want, of course, I don't have to have it to so many decimal places, right? I can round it. So if you want, you can round it to 3 decimal places if you want, right? Or 4 decimal places, whatever. So let's round it to 4 decimal places, these two values here, just to make it a little easier. Just format it and 4 decimal places. All right. There's our critical value of the 4 decimal places for the T. And of course, it's just 1.96, right, for the Z critical value. That's why they use 1.96, is because that's what it rounds to. All right. So what if we wanted to do a confidence interval, right? Could we use Excel here? Yeah, absolutely, right? If we wanted to put in, what do we need? Do we need a mean? We have our means here, right? We have the mean up here. And we have, so this is the sample mean up here, right? Here's a sample mean. Here's a sample. Hold on a minute. No, we could use P1. That would be the sample proportion if we wanted to use a proportion. We have a sample mean, a sample proportion. So we could use these cells here if you wanted to for determining our margin of error, right? Margin of error. All right, so suppose we wanted to do we could use, I'll just use Excel here. You could use a calculator if you want to do it this way. Suppose I wanted to Suppose my sample mean, I'm just going to be, give me a number. Give me any number for sample mean. What's the sample mean?
17.
17. All right, so I'm going to just put 17 here. Forget about all this over here. That means nothing. I'm going to put the, let's say, population standard deviation here. And then suppose I put sample standard deviation next to it. You know the general rule, if you have the population standard deviation, you're going to, hold on one second. We're going to use the, always use the population standard deviation for estimating a mean, all right, if we have it. We ignore our sample standard deviation, all right, and we'll use our Z critical value. But suppose we don't know the population standard deviation, but we know the sample standard deviation. So with a mean of 17, let's make our standard deviation 5, sample standard deviation 5, all right? All right, suppose we want to create a 95% confidence interval, okay? With a sample size of 50. When the mean is 17 and the sample standard deviation is 5. There's no information about a population standard deviation. All right, so we want to figure out so what do we need? What do we need to calculate? Well, we need our margin of error, right? Margin of error. There's our margin of error. Now, how do we calculate the margin of error? It's the critical value times the standard error, right? Where's the critical value? Well, if it's a t, it's right here. This is it, right?
Mm-hmm.
Again, I'm going to put dollar signs around it. Times our what? Standard error. So what's the standard error? It's a sample standard deviation. And I'll put something on that. Divided by the square root of sample size, right? Divided by square root of the sample size. This one right here, I3. There's our margin of error. All right, so it's our critical value, T critical value. Now remember, this is the margin of error for what? Sigma unknown. Okay?
Mm-hmm.
Sigma unknown margin of error, this is what we use. It's going to be I16, which is the T critical value, okay, times the sample standard deviation divided by the square root of the sample size, which is this number here. All right? What if we know sigma? Sigma known. Now, the problem gives us the population standard deviation. What is the margin of error? That's going to be equal to critical value. Now, which critical value are we going to use? We're going to use this one, the Z critical value. times what? Times sigma. Now let's put a number in here. Actually, let's put a number in first. Let's say the population standard deviation 6. All right, let's just say 6. If we happen to know that, this is going to be equal to the z critical value and then we're going to multiply this by what? Population standard deviation again divided by the square root of n, square root of sample size. Again, putting those dollar signs around it. Sure. All right. And there's our margin of error for the two cases. Now the population standard deviation is 6 here. I made it a little bit bigger than the sample standard deviation. I mean, who knows? I'm just putting numbers in, all right? But the important thing is that both of these formulas are correct based on what we've learned. When sigma is unknown, we're going to replace, in this formula here, we're going to use K3, this number here as our sample standard deviation. Okay. And then our critical value is going to be the T critical value, which is in I 16, this one. So I 16 is our T critical value, and we're going to use our sample standard deviation divided by the square root of sample size. If we know the population standard deviation, we're going to use this one, this margin of error here, which is the critical value is going to be the I18, which is the Z critical value, standard normal critical value, times the population standard deviation divided by the square root of the sample size. Okay? And then if you wanted to figure out, you know, the confidence interval, then you could say something like, all right, the lower, we'll call this lower capital O there, lower part of the confidence interval. That's going to be equal to what? The mean minus, now, if the sigma is unknown, we would use this confidence interval, this margin of error here, right? So it'd be this number, A17. And the upper part of the confidence interval, just simply, I could just copy this down and just change the minus to a plus, right? Make this a plus instead of a minus. There's my confidence interval for the sigma is unknown. I'm simply just adding and subtracting the margin of error to the mean. And then so I can copy both of these over, copy and paste here. And what I'm going to do here is I have to change the L from a K to an L here, right? So this gets changed to an L. Right?
Mm-hmm.
And this one gets changed to an L. That's where my margin of error is. And there's my margin of error for the when sigma's known. Okay. So you can set up a spreadsheet like this. So when you're being asked to find these, instead of using software, which will just give you the answer, right? I mean, that's fine. But at least with this, you can understand what you're doing, the mechanics. You're putting the mechanics together. And so I would recommend you learning it this way first before you actually have to worry about, being speedy with it, learn it like this first so that you understand what we're doing. We're simply taking our mean and adding, subtracting this thing called the margin of error, and the margin of error is a critical value times a standard error. Okay. Now in this case, there's symmetry around the mean, right? The distance from the lower end of the confidence interval to the mean is the same distance from the mean to the upper end of the interval, the same distance. And what is that distance? The margin of error. That's why the distance from the lower endpoint to the upper endpoint is twice the distance of the margin of error. If we subtracted these two numbers, we would get this, and divided by 2, we would get the margin of error. Subtracted these two numbers and divide by 2, we would get this number here, the margin of error. Not all confidence intervals are symmetric. I have to tell you that. Some are not. For various reasons, which are way beyond this course, we won't get into. But for this course, that's what we do. All right. Any questions about this? Because that's pretty much it for today. I wanted to show you how to create a confidence interval when sigma is unknown. And you learned about a new distribution called the t, right? And you know to replace sigma with s, the sample standard deviation. But the general formula is exactly the same. And then if you want to set up a proportion problem, you can do that too, right? What do we need for proportions? We need our sample. If we were going to set up a z critical value for a proportion, it's even easier, right? So this is for a mean. I'm going to type in mean here, right? For estimating a mean. Maybe I'll just say estimate mean. Estimate population mean. But if we're estimating a proportion, all right, we're always going to use a z critical value. So we're always going to use this critical value here. All right. So our margin of error, and we always use sigma, and we don't need sigma, right? Because the standard error formula is the square root of the proportion times 1 minus the proportion divided by n, right? Remember that? The standard error for proportion. But since we're estimating the population proportion, we have to replace inside that square root formula the population proportion with the sample proportion. That's what we have to do, right? If we don't know, we're estimating the population proportion, we don't know what it is. Okay, so if we have P1, which let's say P1 here is our sample proportion, P1, right? Sample proportion, because pi is their population proportion. So we use that cell right there for the critical value. So we need a standard error. So, but we need a margin of error. So what do we do? So let's just type in margin of error. And how do we calculate the margin of error? It's the z critical value. So we're going to say equal to this, the z critical value. And then we're going to multiply it by our standard errors, which is the square root of what? P, this one here, our sample proportion, times, in parentheses, 1 minus that, divided by what? N, right? N, which is just this here. Be careful, you're taking the square root of all of it, so don't put square root of that in there. So I'm just going to put the dollar signs around it. And put dollar signs around this. And put dollar signs around this. Close the parentheses. All right, hit enter. Oops, something's wrong. So what was wrong here? So I-18, this one here, times the square root of E6 I3. Did I do something wrong here? I wonder why it's giving me that error message. E6. Oh, that's E7. All right, I see the problem. I put in the wrong cell. So this should be E7. That should be it. But it's still giving me the wrong one. All right. So we have 1 minus. Oh, it was supposed to be E7 here too. Sorry. E7 is where the sample proportion is. That should be right here. Oh, there it is. There's my margin of error. And then my confidence intervals will be, I'll put it right here, lower CI, upper CI. So this one would be the proportion equal to the sample proportion, right, minus the margin of error, right? Let's just put a dollar sign around it, all these. And then I'll just copy the formula down and change the minus to a plus. Change this to a plus. And there's my confidence interval for a proportion. Okay. Pretty wide, actually. Did I do it right? Margin of error is 0.08. Did I do that right? Looks like I did it right?
Yeah.
Okay.
I don't see anything wrong.
Okay. All right. Anyway, that is how you could set up a spreadsheet to do all of this. Any questions?
No.
All right. So I'm going to put that right over here. I'll just put it right here. Estimate. All right. So that's it. As long as you set it up and you understand what you see, then you should be good. So in this spreadsheet, I have probabilities over here where I can calculate probabilities both for means and proportions. Over here, I can calculate critical values and calculate margin of errors, and then give all of the confidence intervals for the 3 cases. So chapter 9, there are 3 cases here, right? Now, there's one more topic that needs to be covered on Monday, and that is the idea of determining your sample size. Did I mention this last time? Maybe not.
I believe so.
Yeah, let me just mention it very quickly. We'll do that also, and also go over sample questions using all this technology, all right? So we'll cover all of that on, not Monday, next Tuesday. And then we'll finish chapter 9. But this question, there's a question that says something like this. Suppose you're a researcher and you want to do some research and do sampling. wouldn't it be a good idea to know the minimum sample size you need for your sample? The question is, how do you determine that? And the answer is margin of error formulas. Margin of error formulas will help you determine the minimum sample size if you determine upfront two things. If you want to determine, number one, what level of confidence you want in the confidence interval, you can determine that upfront, right? And number two, you want to determine how wide your interval, how wide of an interval do you want? You can make that determination up front. And then you can calculate, based on the margin of error formula, the minimum sample size to meet those two requirements. So we'll do that on Monday, and I'll show you how to do it with a mean and how to do it with a proportion. We'll do it both cases, and then we'll do problems, example problems for all of those. So we feel very comfortable for doing confidence intervals. All right, so that'll be what we'll do on Monday, and then we'll finish chapter 9. And then we'll have our Thanksgiving break, right? We'll be off on Thursday. Unless you want to meet on Thanksgiving. I don't think so. All right, guys. So that's it. Any questions? Is that good enough?
Yeah, I don't have any questions.
All right. So again, good luck on the test tomorrow. Now, one thing I do want to mention to you before I stop the recording, because it did come to my mind. I think Han, you would mention, am I going to do another video? Well, I don't think it's necessary, but I do want to mention one thing after I've created the test. Make sure you know all the rules in chapter 5 about probability. What I mean by that is all the basic rules. In other words, know that the probability of an event plus the probability of its complement is equal to 1, which means if we want to find the probability of a complement, we need to subtract from 1 the probability of the event. All right? Remember that? Probability of the complement of an event is equal 1 minus probability of event. Now here's the kicker, and I really do need to mention this to you. And Rose, you're going to hear this too on the video. If I ask you for the probability of some event happening at least once, if I use the term at least once, suppose it's a binomial situation, and you could have up to 10 or 11 things happening, all right, whatever it might be, you know, having you're rolling a die and you're getting a 1, you know. What's the probability of it happening at least once? This is where you would use the complement. You would say that's equal to 1 minus the probability that it doesn't occur at all. All right?
Got it. Yep.
It will come in handy in this test. I will assure you, it will come in handy. All right? So
Can you repeat that again? 1 minus what?
1 minus the probability of something happening at least once is the probability of something happening at least once is equal to 1 minus the probability that it never happens. Doesn't that make sense? Aren't they complements of each other? They are complements of each other, aren't they? Either it happens at least once or it doesn't happen at all.
Right.
All right. So I want you to remember that, because otherwise there's a couple questions in the test that will take too long. So remember that trick. I remembered it when I was taking statistics. It came in handy. Always remember that probability. So I wanted to bring that to your attention because you will need it in this test. All right. So remember, 22 multiple choice questions this time, not 15. It's 22. There's no real long one. They're all. So make sure you don't spend more than 4 minutes per question. It's 4 times 22 is 88 minutes. It's practically 90 minutes. So if you're spending more than 4 minutes on a question, you're spending too much time on a question. Let's put it that way. All right. You know that from exams anyway, right? You don't want to be spending 10 minutes on one question. That would be a very bad idea. It's multiple choice. So if after 4 or 5 minutes you don't get an answer and you're nowhere near the answer, just guess and move on. They're all worth the same number of points. All right. Don't get caught up in saying, I got to solve this. I'm going to solve it until I solve it. And then you realize it's the only problem you solved in the entire test.
Right.
Bad idea. I've done that before. I've fallen in that trap. So don't do that. All right. Anyway, have a nice night and and good luck and have a, and I'll see you next Tuesday. Okay? All right.
Thank you. See you next Tuesday.
See you. Bye-bye.